Hello everyone. In this video, I will introduce operational amplifiers. Operational amplifiers come in the form of ICs. They are typically sold as with the number 741. And as you can see in typical IC for the operational amplifier, you have 8 pins. Each pin has its own function. For people new to ICs or integrated circuits, the way to read pin numbers is you first start with wherever the notch is, and then you start from the top left and go anti-clockwise. So for example, here's the notch. I start here, this is pin number 1, and I'll be have 2, 3, 4. This is pin number 5, 6, 7, 8. Sometimes they also give you a dot like this, which shows where the pin number 1 is. In a circuit diagram, operational amplifiers are represented using the triangle symbol as shown in this circuit here. A typical application of an operational amplifier requires two power supplies. Sometimes you can get away with just one, but in most circuits you have two power supplies. The positive power supply will be connected at pin number 7. The negative power supply will be connected at pin number 4. Note that unlike resistors, operational amplifiers are active devices. That means, for example, resistors cannot supply their own power. But operational amplifiers, because they are connected to our power supplies, they can draw power from these power supplies and they can generate their own power that way. Since they have a power source connected to them, operational amplifiers are typically called active devices, whereas resistors are, or in fact even capacitors or inductors are passive because they don't have a power supply. An operational amplifier has two input pins and one output pin. One of the input is a non-inverting input denoted by a plus sign, and another input is an inverting input denoted by the minus sign. The reason for why they are called so will be apparent soon. And pin number 6 is the output pin. The next thing we want to see is what is the relationship between the input pins or the voltage of the inputs to the voltage of the output. Since we have our simulator, we can just make a DC sweep and see what happens. Since I have two inputs, I will test one input at a time. So that means first I will ground my pin number 2, which is the inverting input, and change the voltage at pin number 3 and see what happens with the output. Then I'm going to ground pin number 3, change the voltage at 2 and see what happens with the output. I connected a ground at pin number 2, a voltage source at pin number 3, and I have connected a probe at the output pin number 6. I want to do a DC sweep, so I will go to the settings here and select DC sweep. I want to change V4, so I will select my source as V4. I'm changing V4 from -1 to +1 with increment of 0.01, and the output is selected as a voltage probe at the output pin, which is pin number 6. So let's run the DC sweep here. This is what we get. So what are we seeing here? So when the pin number, the voltage at pin number 3, let me put this. When the voltage at pin number 3 is negative, the output voltage is like -11 or something. And when the voltage at pin number 3 is positive, the output voltage is +11 or something. So it seems like this is acting like a threshold, right? So if the input at the non at the input if the input voltage at the non-inverting input is negative, the output will be negative voltage. And if the voltage at pin number 3 is positive, the output will be positive some voltage. Let's try to zoom in around 0 and see what's really happening here. So if okay, let's say reset, zoom in. Okay, I'm gonna zoom in around here. And as you can see, in a very small area, or a very small interval, close to 0 volts, it's actually acting like a linear amplifier, right? So the voltage at pin number 3 is changing very little, but the voltage at the output is changing by drastically, right? So this is like millivolts here, but this is like volts. So in a very small region around 0 volts, the operational amplifier is acting like a very high gain linear amplifier. I can use the cursors to check the slope, and it is showing me dy by dx, which is the slope of that line, is about 2.22k, which is 2223. So that's a very large gain. Also, note that the slope is positive. That is why the input at pin number 3 is called non-inverting input, because the slope is actually positive, it's not inverting. And since pin number 2 is called inverting input, that which would probably mean that if I do the same thing at the pin number 2, I will get a slope which is negative. And that is why pin number 2 will be called inverting. So let's see that. This time I connected non-inverting input to ground, and I connected the voltage source at the inverting input. So now we can change this voltage V4 and see how the output responds. So let's open up the DC sweep. Source is V4, which is what we want, -1 to 1, increment of 0.01. The output is selected as the voltage probe, which is at the output pin. So if I run this DC sweep, this is what I get. As you can see, this time the slope is negative, and I can also calculate the slope using the cursors in basically whatever was when we had the non-inverting configuration, where we had 2.22 thousand as the gain. This time this is minus 2.22 thousand as the gain, right? So as you can see, since the slope is negative, pin number 2 is called the inverting input. Okay, and also notice that the gain is very high, and therefore the linear region of operation, when the gain is so high, is in a very small interval. Again, I want to bring your attention to the fact that the x-axis is in millivolts, the y-axis is in volts. Now let's consider the mathematical modeling of what we saw so far. Here is a symbol for the operational amplifier. We have two inputs, the non-inverting input and the inverting input, and we have an output. When we set V minus as 0 and we changed V plus, we saw that the output VO was A times V plus. A small caveat here. Note that when you look at the graph, the output is not 0 exactly when the input is 0. In fact, there is some shift here. In general, when you have a straight line, the equation for the straight line will be y equal to mx plus c, where x is the x coordinate, y is the y coordinate. And when the input x is 0, if the output is not exactly 0, then the c will not be equal to 0. So what that means is, here when we are saying VO is A times V plus, there should be a plus C here. But for now, we will assume that C is 0. And the reason is, in our simulation, there was a bias in op amps, and that's a more slightly advanced topic. So we're going to assume that C equal to 0. That is, we make sure that the op amp is configured properly, so that we make C equal to 0, right? So from going forward, we just assume that, okay, if the op amp is configured properly, which will be the case when for an ideal op amp, then the output will be just A times V plus when V minus is set to 0. We also saw that when we set V plus equal to 0 and we changed V minus, the output VO was negative A times V minus, where A was about 2.2K. Now here is an interesting point. The way the internal circuits in the IC are designed, it makes that operational amplifiers are actually, they behave like linear circuits. That means we can write our output VO as some C1 times V plus C2 times V minus. Using these two observations here, we can say that C1 should be equal to A and C2 should be equal to negative A. So which brings this equation to be, my output VO is A times V plus minus A times V minus, which is basically equal to A times V plus minus V minus. This means the operational amplifier is a difference amplifier. This means it amplifies the difference between the two inputs. So that output is be some big gain times the difference in the input voltages. In our discussion here, we were assuming the operational amplifiers are linear circuits, which is true in most cases, but there are some caveats. So we will discuss those caveats now. We saw this plot when we set V plus equal to 0 and we changed V minus. And we did a DC sweep. We were plotting V minus on the x-axis and VO on the y-axis, and this is the plot we have. Here we can see that the operational amplifiers acts linear only in a small range of input values. That means all this discussion here happens only when the difference between the input pins is in this small range. When the difference between the input pins goes outside that range, then the output no longer changes linearly with the input. When the op-amp is behaving non-linearly like this, we will say op-amp has saturated or op-amp is operating in saturation. This saturation typically happens when the output is close to power supply, and in general when the output is power supply minus approximately 1 volt. So if you want to operate the operational amplifier in the linear region, you want to make sure that the output voltage does not get close to the power supplies. So let's summarize what we have seen so far in this video. First, we explored the op-amp in Multisim. We performed DC sweeps to see the relationship between input and output. We saw that the op-amp needs two power supplies, and we derived the operation of the amplifier of the op-amp as a difference amplifier, assuming linear operation. We looked at the linear and non-linear operations uh, in the DC sweep plot. And then we discussed the relationship between the output and the power supplies and how that determines whether the op-amp is in linear or non-linear behavior. Here are some multi-sim exercises you can do to get your hands dirty with the operational amplifier and get a feeling for it. And we will do some more multi-sim exercises in the lecture.